Good day everybody. Welcome to this presentation. I am Captain Ronnie Rani. In this video, I will be explaining the solution to problems 6 and 10 from Captain Subramaniam's textbook, Ship Stability 1, on the topic of water pressure in exercise 2. The problem states a collision bulkhead is triangular in shape. The black triangle shape that you see is your collision bulkhead. Its maximum breadth is 12 meters and its height is 15 meters. The maximum breadth is 12 meters and its height is 15 meters. We have to find the thrust experienced by it if the forepeak tank is pressed up to a head of 3 meters of salt water. The pink dashed triangle that you see in the background is the forepeak tank, which is extending to a height of 3 meters over and above the height of the collision bulkhead. That is why it is said to be pressed up to a head of 3 meters. If you look at the diagram here, the next slide, you have the forepeak tank, you have this collision bulkhead. This collision bulkhead is up to a height of 15 meters given in the problem. But the forepeak tank has been filled up to a height of 18 meters, thus having a head of 3 meters over and above the top of the collision bulkhead. I'll take you to another slide. This one here is a three-dimensional picture of the forepeak tank, insides of the forepeak tank. The triangular shape that you see with the red line and the red dashed line at the top is your forepeak tank. There is the collision bulkhead, which is the aft bulkhead of your forepeak tank. Okay. Now, the collision bulkhead could be exactly the same height as that of the forepeak tank, or it could be higher than that, and higher than the top of the forepeak tank, or lower than the top of the forepeak tank. It all depends on the construction of your ship. So as given to us in this problem, the maximum height is 15 meters and the tank is filled up to a head of 3 meters. That means that the forepeak tank is extending further up over and above the collision bulkhead by 3 meters. This is as per the drawing that I have shown you. The red dashed line at the top is extended further up by 3 meters. To the problem. The breadth of the collision bulkhead is 12 meters. Water is pressed up to a head of 3 meters, that is the height, and the height given is 15 meters. Now for a triangular shaped body, the pressure is taken to be at 2/3 the height from the apex which is pointing downwards, or 1/3 from the baseline. So in this case, it is 1/3 from the baseline is 5 meters. But you have a head of 3 meters. Thus, in this case, we have to calculate the total height of 8 meters. 3 meters plus the location of the centroid of your collision bulkhead, which is 5 meters from the base, thus giving us a total height of 8 meters. Pressure is equal to depth into density. That is 8 meters is the depth, and density of the water in the tank being salt water is 1.025, giving us pressure equal to 8.2 metric tons per square meter. Area of the triangle, half base into height. Base being 12, height being 15. The area of the collision bulkhead is 90 square meters. Thus, the thrust experienced at by the collision bulkhead at its centroid is equal to pressure into area equal to 90 times 8.2 equal to 738 metric tons. Now coming back to the same problem, it could also be given as that there is this four-peak tank, okay, and it has been pressed up by another 3 meters. That means that there is additional water in your air pipe and sounding pipe to a height of 3 meters within it. Even though the volume and the mass of this liquid within this air pipe and the sounding pipe is very, very minimal compared to the volume of the liquid within your four-peak tank. It is to be assumed as if that there is a virtual tank sitting on top of your four-peak tank. The four-peak tank is given by the black triangle, and this virtual tank is given by this trapezoid, the pink dashed line sitting on top. Let me again by drawing another shape for you. Let me take this shape. So this is the virtual tank that is sitting on top of your four-peak tank. Or you can say that this an actual physical tank is existing on top of your four-peak tank. So the height is from the top of this tank equal to 5 meters plus this height of 3 meters. The solution is exactly the same. Even though the volume of the liquid within this air pipe and sounding pipe is very, very minimal, the answer to the thrust, to the pressure and the thrust experienced at the centroid will still be equal to 738 metric tons. Coming on to problem number 10. A double bottom tank measures 25 meters by 20 meters by 2 meters. Find the thrust on the tank top when pressed up to a head of 16 meters of salt water. Also find the resultant thrust on the tank bottom and the direction that it acts if the ship's draft in salt water is 10 meters. As per this drawing that I have on my screen, you have this double bottom tank 20 meters by 25 meters by 2 meters in height, and there is the tank is pressed up to a head of 16 meters. That means over and above this 2 meters, which is the height of the tank, there is in the air pipe and sounding pipe water filled up to a height of 16 meters. The ship is floating at a draft of 10 meters. This is WL is the water line, and below the water line you have the ship extending down to a depth of 10 meters, of which 2 meters is the depth of your double bottom tank. Thus, from the top of your double bottom tank to the water line, you have a depth of 8 meters. Let me explain this to you once again with a two-dimensional drawing. In this picture on the top left-hand side, you have your double bottom tank, which is 2 meters in height, and there is a head of water extending up by 16 meters over and above the tank top. The ship is floating at a draft of 10 meters. Thus, the height or the depth from the water line down to the tank top is equal to 8 meters. Now, because of this head of water extending above the tank top of 16 meters, it is as if there is a virtual tank sitting on top of your double bottom tank, as shown in the picture on the right hand side at the top. This is just an imaginary tank that is sitting on top of your double bottom tank. Even though it is not there, but the water is just in your air pipes and sounding pipes, it is as if that there is a virtual tank sitting on top of your double bottom tank and it is full. The volume of the liquid within the volume of the salt water within the air pipe and the sounding pipe is very, very small in comparison to the volume of this virtual tank sitting on top. But it is as if it is present and it is exerting the same pressure on the tank top and the tank bottom. Height above the tank top is 16 meters and above the tank bottom will be 16 plus 2 equal to 18 meters. If, coming to the picture at the bottom left hand side, if the air pipes were empty and the sounding pipes were empty, the thrust experienced by the tank top would be equal to 0, because there is no water, there is no liquid within the air pipe and the sounding pipe extending above the tank tops. The pressure and likewise the pressure and the thrust experienced at the bottom of your double bottom tank would be just that of 2 meters. As you see in the picture on the right hand side at the bottom, the virtual tank is empty. Thus, there is no pressure on your tank top, but the pressure existing on the tank bottom is only of 2 meters height. So coming to the solution now, we have pressure on the tank top equal to depth into density, which is 16 times the density of the relative density of the water inside the tank, which is salt water. That is giving us 16.4 metric tons per square meter. The area of the tank top as well as the tank bottom is equal to 25 into 20, that is 500 square meters. Thus, the pressure on the tank top is equal to 500 into 16.4. Pressure into area is equal to 8,200 metric tons. Pressure on the tank bottom also equal to depth into density, but here the depth is 16 plus 2, that is equal to 18 times 1.025 equal to 18.45 metric tons per square meter. Thrust on the tank bottom, pressure into area, giving us 500 into 18.45 equal to 9,225 metric tons. Now, we know that the pressure acting on the outside of the tank bottom, that is on the keel. That is on the keel. I can show you with these two arrows. This is the pressure acting up on the tank bottom. Is equal to depth into density. Now, depth over here is the draft. and the draft given to us is equal to 10 meters multiplied by density, giving us an answer of 10.25 metric tons per square meter. Thrust is equal to pressure into area, equal to 10.25 into 500, equal to 5125 metric tons. Thus, the resultant thrust is the difference between the thrust acting from the top as well as the thrust acting from the bottom. The thrust acting from the top is 9225 metric tons and the thrust acting from the bottom is 5125, giving us the resultant equal to 4100 metric tons, and it is acting downwards from the greater to the lower. Now assuming that, let us assume as another part of this problem that there is no head of water. This air pipe and sounding pipe, which were filled with salt water, are now empty. Okay, as I explained to you here in the bottom two drawings, that the air pipe and the sounding pipe are empty. Thus there is no water pressure acting on the tank top. This virtual tank is empty. The only water pressure that is acting is on the tank bottom, which is at a depth of 2 meters. As you go through this problem, solution to this problem, you will see that the resultant thrust on the tank top is equal to 0 and the resultant thrust acting on the tank bottom is equal to 1025 metric tons. The thrust acting on the tank bottom from the sea is equal to 5125 metric tons, and the resultant thrust is the difference between the two, that is between 5125 and 1025, equal to 4100 metric tons. But in this case the thrust is acting vertically up from the greater to the lower. Thank you very much for your attention. Please give me a like and a thumbs up. Share my video sorry, and also subscribe to my channel. Goodbye.